All right, guys, this is where we left off. We were talking about our compound X that we know the empirical formula is C3H5N. It says it is determined that 25 gram sample of compound X contains 9.11 times 10 to the 22nd molecules. 1 second. Calculate the molar mass of the compound compound X in units of grams per mole. So the way that I see this is if we want 2 units, we have to start with 2 units. So basically it told me that 25 grams is equal to that many molecules. So I'm going to say I want grams over mole. So I'm going to start with, that's what I'm looking for. So I'm going to start with the 25 grams and I'm going to put it over what it's equal to, because anytime we have something that's equal, if 25 grams in this situation is equal to 9.11 times 10 to the 22nd molecules, anytime we have something that's equal, we can make it a fraction, because that would equal 1 if we divided both sides by that 9.11 times 10 to the 22nd. That's what we get. So we can use this the same way we would the other measurements. And then we have grams on top, so that's good, but we really want to get moles on bottom, so we need to get rid of our molecules. What do we know about molecules? That 6.02 times 10 to the 23rd of them is equal to 1 mole. Now we have molecules canceled, and we have grams and moles on top and bottom. So then we can just solve. If you solve that, you get 165 grams per mole. So that would be the answer to that question. It says based on your answers to part A and B, sorry, I'm reading as well. Determine the molecular formula of compound X. So the way that we do that, it says the ratio of the molecular formula to the empirical formula is a whole number that is equal to the ratio of the molar mass divided by the empirical mass. So we know that our molar mass is the 165 that we just found, and our empirical mass, we can find that. We said that it was C3H5N. So 3 times 12 plus 5 times 1 plus 14, and you should get 55 roughly grams per mole. So if this is our empirical mass, then the ratio is the molar mass divided by the empirical mass. So the molar mass divided by this 55, and you get 3. So what that means is we're going to take 3 and multiply it by our subscripts on our empirical formula to get our molecular formula. So it'll be C9H15 and 3. And that would be our molecular. And if you wanted to check yourself, you could find the molar mass by saying 9 times 12 plus 5 times 1 plus 14 times 3. And you should get 165. Okay, so we're switching to a different concept. It's the same thing. We're just going to be looking at examples of when we can use these. So we know that combustion follows this formula. That formula meaning that it's some type of carbohydrate, where the CHO is variable, like this indicates right here. And we know that combustion is going to include oxygen or fire won't happen. And then we yield carbon dioxide and water vapor. You could also make combustion with different compounds, such as nitrogens and sulfur compounds. You just get different gases. So we could do the same thing. We have our problem right here. So a sample of a compound that contains carbon, hydrogen, and oxygen is burned completely in oxygen. Data from the combustion experiment is shown below. So in the experiment, or in the table, we have mass of our sample that is burned. So we start with 5 grams. That would be of this right here, of your unknown sample. Your mass of carbon dioxide that's produced, so our mass of our carbon dioxide is 10.99, and your mass of water vapor is 6 grams. So this is just kind of restating it with the table rewritten. It says determine the mass of carbon present. So we know that we made 10.99 grams of carbon dioxide, and we want to know how many grams of carbon so that we can then the goal eventually will be to transfer that into moles. Because if you remember correctly, the step 1 of empirical formula is to find, that's an M, it's cute, is to find moles of each. To get to moles, first we have to have grams. Normally you're given the grams. In this situation, you're given grams of a product, and you have to figure out how much carbon was made into that product. So you're going to use the mass fraction. Mass fraction is the mass of carbon over the mass of your compound, which in this case is carbon dioxide, because that's the one that has the carbon. So we're going to take 12.01 grams of carbon over 44.01 grams of carbon dioxide. Notice that your grams of carbon dioxide do cancel, and you only are left with grams of carbon, which is the goal. So if you do that math, you get 2.99 grams of carbon. The long way of doing this, if you want to think about it and like why we use the mole fraction, is we take the 10.99 grams of carbon dioxide, and we know that our, I want to make that over here. We know that our goal is grams of carbon, so let's just work that way. Dump what you don't need, grams of carbon dioxide. Well, what do I know about grams? I know that 44.01 grams of carbon dioxide is equal to 1 mole. This is the molar mass. Okay, and this is carbon dioxide. I want to get to carbon. So once we're in moles, that's when we can transfer from one thing to another. So I know that 1 carbon dioxide holds, oops, come on thing, holds 2 moles of carbon. Nope, that's silly. That's silly. It holds 1 because of that subscript of 1 right there. 1 moles of carbon, and then I can say, this is moles. Mole of carbon equals 12.01 grams of carbon, and then you should get the same number right here, 2.99. Okay, then we also want the mass of hydrogen. Now, which one of these products, oh, it's right here. Which one of these products has hydrogen? Well, the mass of water. So we're going to use that one in the same concept. 6.00 grams of water. Let's use the mass percent, or the mass fraction, grams of water, and I can get my grams of hydrogen. Just remember that this is grams of hydrogen in water. So it's going to be like 2 times the typical gram, because this is our mass fraction of hydrogen. So it's mass of hydrogen in water, so it would be times 2, because there's 2 hydrogens, over the mass of water. Whew, okay, trying to talk too fast. 18.016 is the mass of water. If you wanted to find that, this is the molar mass. Remember, you find that by saying 2 times the 1.008 for hydrogen and 1 times 16, and add those together. And you, 2 of those 2 hydrogens would be 2 times 1.008, which is the same thing as 2.016. Your water cancels, you're left with grams of hydrogen, and it would be 0.671. And then mass of oxygen present, you have oxygen in 2 different places. So the easiest thing to do is just to understand that you started with 5 grams, 5.00 grams, and you made 0.671 grams of hydrogen. You also made 2.99 grams of carbon. So what's left has to be your oxygen grams. So if you do that, you should get 1.33 grams of oxygen. All right, now we're back to where we started. This is a thing that we actually know how to do. So find the moles of each. So 2.99 grams of carbon. Find the moles by saying gram to mole. Is it 0.1? Yeah, 0.1. Do that math and you get 0.2497 moles of carbon. If you do it with hydrogen, you had 0.671 grams of hydrogen. 1 mole of hydrogen, it's 1.008, which gives you 0.666, that makes me uncomfortable, moles of hydrogen. Do the same thing for oxygen, 1.33 grams of oxygen, molar mass, grams of oxygen equals 1 mole of oxygen. This is 16. So you end up with 0.0831 moles of oxygen. To find the empirical formula, you then divide every number by the smallest, which would be this one. So every number is going to be divided by that 0.0831. Okay, and then you end up with your ratios. So when you do that, you get 3, 8, and 1. So your empirical formula would be C3H8O. Okay, another type of situation is with hydrates and salts. So let's just read this together. Another type of situation that involves mass and mole ratios involves a substance known as hydrate. Y'all have asked me what that is before. Well, now I'm telling you. A hydrate is a substance in which water molecules are included in the chemical formula. These substances are often ionic compounds in which the water molecules are bonded to the ions in a crystal structure. A hydrate salt can be heated to remove the water through evaporation, forming an anhydrous salt. 2 examples of hydrous salts and hydrates are listed in the sample below. So copper 2 sulfate would be this. Copper 2 sulfate, pentahydrate, you put a raised dot, penta means 5 waters. Calcium chloride, CaCl2, same concept here, CaCl2, raised dot, di means 2 waters for dihydrate. Okay, and then we're going to calculate our mass here. You do the same concept. I don't know that I necessarily need to walk you through all of these steps, but I can. So it says calculate the mass of copper sulfate present in 25 grams sample of the copper 2 sulfate pentahydrate. So I need to know the molar mass of the copper 2 sulfate and the molar mass of the copper 2 sulfate pentahydrate. So you can trust me that this is 159.61. I believe that y'all can do that by now. And then same thing, but of the copper sulfate, you're going to add 5 waters to this. So 5 times 18 plus the 159.61 gives you 249.69 grams per mole. And then if I want to know the amount of copper sulfate, I'm going to take what I have, 25 grams of the copper sulfate hydrate. So this is the hydrate version. And I want to get to grams of copper sulfate. So this is where I'm going to use these two numbers. I can say 249 grams of 249.69 grams of the hydrate contains 159.61 grams of copper sulfate. And then you solve. This would give you 15.98 grams of copper sulfate. Sorry, y'all, I'm in a hurry, so I'm kind of going through it fast. The next one says calculate the mass of water present in that. Just subtract. 25 grams is what we started with. Subtract that 15.98 grams, that is the copper sulfate, and you get 9.02 grams of water. And then it says calculate the percent of water by mass in the hydrate. Okay. Hold on, I'm looking at what I did, and it's not making any sense. Oh, it's because this is a different problem. But if I wanted to do it by this one, I would just say my total percent of water would be, there's 5 waters, so multiply that by the molar mass of water, which is 18.016. Put that over the total mass, which is the big thing, 249.69, okay, times 100, and you should get your percent. All right, let's talk about the lab example. This is really where I've been trying to get. I don't know that I'm going to do the math because I'm running out of time, but I do want to show you how this, I want to talk about how this works, because we'll be doing a lab like this. In a certain experiment, a sample of a hydrate of magnesium sulfate, MgSO4N H2O, is heated in order to remove all the water from the sample. Experimental data is shown below. So here we have our table. We have our mass of our empty container. We have the mass of our hydrate before heating, and then we have 3 consecutive heatings. This is how we would do that. We would put our hydrate salt in a crucible. We would heat it using our Bunsen burner, and then after all the water is gone, we're left with a solid salt. So the first one says, explain how the data indicates all of the water has been removed from the hydrate salt in this experiment. I'm going to stop here. I want you to think about this, and I want you to answer this question and the rest of this when we get back to class. Okay, sorry this is rushed. I hope that helps. Answer the rest of the PowerPoint before class.